How does principal component analysis, PCA, reduce dimensionality? Imagine you have a huge collection of data with many features, like hundreds of measurements or characteristics. It can be overwhelming to analyze all those details at once. That is where principal component analysis, or PCA, comes into play. It helps simplify this complex data by finding the most important patterns. PCA starts by shifting the data so that its average is at 0. This step makes it easier to see how features relate to each other. Next, it calculates something called the covariance matrix. Think of this as a way to measure how two features change together. If they tend to increase or decrease at the same time, they have a strong relationship. After that, PCA finds new axes, called principal components. These are like new directions in the data space. Each principal component is a combination of the original features, but they are constructed to be uncorrelated with each other. The first principal component captures the most variation in the data, meaning it explains the biggest part of what makes the data different. The second principal component then captures the next largest variation, but it is at right angles to the first one, so it adds new information. By ranking these components based on how much variation they explain, PCA allows us to pick only the top few that cover most of the important details. For example, if the first 3 components explain 95% of the variation, we can just use those instead of hundreds of original features. Once we select these top components, we project the original data onto them. This process reduces the number of dimensions, making the data easier to visualize and analyze. It also helps machine learning algorithms run faster because there are fewer features to process. In the world of artificial intelligence and machine learning, PCA is a key tool for unsupervised learning. It is especially useful when working with images, text, or complex data from models like ChatGPT, DALL-E, or Midjourney. For example, in image creation, PCA can compress the data, speeding up training and making it easier to interpret. But it is important to use PCA carefully. If not, it might remove some important information or introduce bias. Understanding how PCA transforms data helps us decide what to keep and what to discard. To sum up, PCA reduces the number of features by finding new, uncorrelated axes that capture the most variation. This way, we keep the core information while making the data simpler to work with. It is a fundamental step in many machine learning projects, especially when dealing with large, complex datasets.